So for the example related to the extending trig functions to vectors, we have ourselves two pieces of information. The vector A's magnitude, the length of the arrow is 7, and the vector is at an angle of 120 degrees off the positive x-axis. So the first thing we should do is sketch the vector. And that vector is at 120 degrees off the positive axes. And so we have our vector here, and that vector is A, and its length is 7, and it's at 120 degrees. So then how can we use what we've learned about right triangle geometry and sine and cosine and tangent in order to be able to say more, that is to find the actual position vector for A? Well, we're going to need to create a second sketch. And that second sketch is going to be a right triangle that we can then apply our trigonometric functions to. So the right triangle we're drawing here is this one with a hypotenuse of 7. We're interested in A's x component and A's y component. And we know that this angle right in here must be 60 degrees because these two angles, 120, and this interior angle must add up to 180 degrees. So just to be clear, this triangle is coming from right up here right? So I'm thinking about a triangle that I wasn't given in order to give me the information I need to answer the question I'm being asked. All right, well, let's jump right in then. So the third thing we're going to do is find AX and AY. So let's find AY. From the perspective of the angle 60 degrees, AY is opposite. So we want opposite, we have hypotenuse, and so we're going to use sine. The sine of pi over 3, which is 60 degrees, right? So I'm thinking about this triangle here in the second sketch. The sine of that 60 degrees, or pi over 3 radians, is the y component of the vector divided by 7, the magnitude. Again, AY is opposite, 7 is hypotenuse, and so we can substitute in now our value for the sine of pi over 3. And we can solve that, and AY is equal to 7 root 3 over 2. So we now know, right, this is the length of this side right here. Or this is, yeah, well, it's the length, there you go, exactly, of that side right there. All right, so then the fourth thing we need to do is, I guess this is kind of like 3-1 and 3-2, but the fourth thing we need to do here is find AX. And so from the perspective of the angle 60 degrees, AX is adjacent. And we know the hypotenuse, so we can use cosine. The cosine of that angle, pi over 3, is equal to AX, the adjacent side, divided by 7. Substituting in 1/2 for the cosine of pi over 3, we find that AX is equal to 7/2. All right, so we now know these two lengths right here. But we now need to zoom out a little bit and remind ourselves of the bigger picture that we're trying to talk about. All we know is these values up here, right? So this value, let me find it here, the AX is 7/2, so this value right here is 7/2, and the AY is 7 square root 3 over 2. But if we think about the actual vector, remember the vector has direction component, and so it's important that when we talk about what the vector is in quadrant 2. And in quadrant 2, the x values are negative and the y values are positive. So if we think about kind of what this vector is doing, is it's going left and up. The left needs to be described. So the fifth thing we need to do is describe the vector A. The vector A is, and maybe what we'll do is we'll say, well, that's negative AX, positive AY, and why is that? Because A is in quadrant 2. Right? So the AX we found is the length of that side of a right triangle, but in the context of the vector, it's a negative number. And then the AY, because it's in quadrant 2, is a positive number. All right, so I'm trying to give an example of a great solution here, and that's just notes to myself, so I'll erase that. And then we have that's negative 7/2. Oops, let's... Negative 7/2 and 7 square root 3 over 2. And so we have found the vector that has a magnitude of 7 and that is pointed 120 degrees off of the positive x